his name? That's right. What are you doing? Make it That's really
Okay, well, welcome to the discussion panel. My name's Ursula Martin. I'm an academic at Queen Mary University of London, on sabbatical in Edinburgh. And we're sort of making this discussion panel up as we go along, I think. And it's only half an hour, and I can see the clock, and the panel can see the clock, but you can't see the clock. Perhaps you've got more issues. We thought how we'd organise this session is, well, we've had a number of talks today, starting, of course, with Joseph's talk this morning about the very nice work that he's been involved in with his colleagues, and then various other people have touched on this, including hearing about Catherine's work. So we thought we'd start by just asking everybody on the panel, first of all, to remind us who they are, and then to say just a little bit about machine learning and automated reasoning. Is it a good idea? Why might it be a good idea? Why might it not be a good idea? And then after that, we actually want to get some audience discussion going. And of course, this is a research students workshop, so hands up everybody who's a research student. Yeah, all right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, so that means we've got to have 12 research student comments before anybody else is allowed to say anything. Because some canny people knew what was coming, and when I said hands up if you're a research student, I might see something bad. But it'll be fun to hear, because the research students, there are people in this room who've been in this field for a heck of a long time. There are people who's old enough to remember programming on punch cards. Yeah, there you go. Well, we're the real old folks, Ask your granny what a punch card was next time. But, we've been around an awful long time. But actually, sometimes for the people who've been around an awful long time, we're the ones who get stuck in our ways of thinking. And then the PhD students come along and say, well, why couldn't you have a theorem prover on your iPhone? Why couldn't you? Why can't you do verification in Facebook? People come along with completely new ideas, and so this is about hearing people.
Why can't we stop using punch cards?
Well, that's a different question. That is Saturday morning's panel discussion, led by Alan Frisch. Okay, so machine learning and automated reasoning. Is it a good idea, or why might it not be a good idea? It's very quick. Joseph, please start.
Oh, I thought ladies first. Okay, so you heard my talk. So so to introduce myself again, I'm Joseph from University in Nijmegen in the Netherlands. And yeah, I think that, well, to say that it's a good idea, well, maybe that's an overstatement. Maybe you want me now to say something like it might not be a good idea in some cases, or what exactly, what kind of machine
I want
learning?
the elevator pitch. I want you to.
Sorry?
I want the elevator pitch. You have certain. You know the phrase elevator pitch?
No, I'm not.
30 seconds.
So-
We've got 30 seconds.
Oh,
You've got 30 seconds.
Oh, it's just 30 seconds. Oh,
Well,
okay.
you've got a very short time to sell your brilliant idea to somebody who's got millions. It's
Oh,
like
so-
writing a grant proposal, but it's 30 seconds in an elevator. That's the
Yeah, so basically the elevator pitch for me has been, I don't think we can do advanced theory proving without complementary methods like machine learning. I think that's not how humans work, and humans can do much more in mathematics these days than computers can do. So, well, you obviously will find counterexamples like the Robbins conjecture, but even for Robbins conjecture, will make you really a huge amount of tuning of this software to do it. So you could argue that even he was using the data-driven methods in some sense. So I think, well, we cannot do exhaustive brute force search and get to Brouwer's fixed from Fermat's last year. So something else has to be done. Machine learning is one of the things which matters. That's my opinion.
Okay, so I'm Alison Hughes from Queen Mary, University of London, with Ursula, soon to be moving here to Dundee. And my background in this area is in using inductive logic programming to build systems which can take in a little bit of knowledge. Usually they're in Prolog or Java, these systems. Take in a little bit of knowledge, like a few objects, a few basic concepts in mathematical theory, like addition, concept of a number, some very basic things, addition, multiplication, and so on. And then the systems use production rules to make these simple concepts into a little bit more complicated concepts. And this cycle cycles over. There are evaluation criteria for seeing whether these concepts are interesting or not, and then conjectures are formed automatically about relationships between concepts. And from this very basic sort of input, you can get interesting new mathematical concepts. So far, not very, very interesting new mathematical concepts, but interesting enough to be published in the Encyclopedia of Integer Sequences. So that kind of level of things. Likewise with conjectures. I think nothing groundbreaking new has been found yet, but we've recreated some very interesting ones like Goldbach's conjecture. The sort of concepts that are coming up with the prime numbers or refactorable numbers, which is where the number of divisors of a number is itself a divisor of a number, like 8, which has 4 divisors and 4 divides 8. So that's my take. The answer to Ursula's question is yes, and in the context of producing new concepts and conjectures rather than focusing on proofs.
Well, I'm interested in machine learning for interactive theory proving, and this is slightly different from what Joseph and Alison are interested in. So I'm not interested in automation of proofs, not at all. I'm interested in using machine learning to actually help people to deal with interaction with theory provers. So when we talk about POC or SS-reflect or similar systems, a lot of programmers' work is interacting with the theory prover. And actually making this experience more interesting, more user-friendly, maybe more productive is my interest. And about a year ago, a couple of years ago, when I was writing this proposal on which Jonathan is now funded, I was running around asking at every conference when I could find a Koch person or an SS-reflect person. Well, Koch SS-reflect is of course most famous for Georges Ventier's results in four-color theorem. And nowadays, Jonathan, they're doing Fay-Thompson theorem. So people who really do serious mathematics, a lot of it in interactive theory proving. I was coming to them and asking the same question, is it any good? Is it any good that I write a proposal? That was a practical question for me. Would you be interested if I write the proposal, win the grant, and then bring a paper about this to you? I was expecting them to say, nah, we hate AI, because you always hear people from theory proving say AI is a black box approach to like constructive theory, clear rules, and so on. And they, surprisingly, they all say, yes, it's a very good idea, because indeed when you prove big libraries, you feel like I'm proving something that I would have proven a week ago. But obviously the library is too huge for you to go and manually trace what you've done a week ago. So you end up actually rediscovering this result. And they said, we don't believe your machine learning would ever help us to really prove new theorems. But if you can do it handy and fast enough so that it would suggest me, if I have a feeling that I've proven this already, I press a button and it says, yeah, you've actually passed through these steps in demo 1, 2, 3, 4. And they said, well, this tiny addition would actually help us as users. And this is exactly what we went for when Jonathan came. And so it was a very small goal in a way, but we wanted it to be user-friendly.
Okay, great. Well, now let's throw it over to the audience. If you're a big fan of machine learning, put up both hands. If you're a medium fan, put up one hand. If you're not a fan at all, just put up no hands. Who's a big fan of this kind of approach? Oh yeah, look, two. How many two hands have we got? We've got some 1.5 hands. That's, we've got. No, everybody's very sitting on the fancy. Yeah, we've got some. Who's a 2-hand person? Yeah, there's a 2-hand person. There's a 2-hand. I can see about 3 2-hand people, and where's Jonathan? Surely a 2-hand person. Oh, he's in the front. He's a shy 2-hand person. I see a bunch of 1-hand people, and I can see some. Oh yeah. Oh yeah.
Every time you ask, you
I can see about 10 or 15 1-hands people, and then there were some no-hands people. Was there a no-hands PhD student? You at the back, you were a no-hands. Were you a no-hands PhD student?
I'm not a PhD student.
Oh, well, who's a no-hands PhD student? Who's a not really sure PhD student? Yeah, go on, you're in the middle back, yeah. Yes,
Brian.
you. Yeah, Brian, yeah.
What am I commenting?
Yeah, you're not really sure why people are so excited about machine learning.
Well, it's more that I don't know enough about it to give a reasonable response.
Yeah. What would sort of convince you? You know, whatever it is you're doing, what would make you say, hey, wow, I should add machine learning to what I'm doing?
So I didn't put my hand up because I don't really know enough about machine learning. I suppose I wouldn't have thought to apply it to my field, but I can see how it could be a field. So I really don't have much to say on particular.
What is your field then?
I'm doing formal methods for agent-based learning systems. So work with model checkers and so.
So in fact, we haven't had a talk about it today, but there are people doing exactly applying these techniques in formal methods in area 1. So somebody else, another PhD student who wasn't sure, was a bit sure.
I didn't raise my hand. I was
You're
discussing
waving.
with my friends outside, and I wasn't sure how this would help because all the proofs are different, and in real world I couldn't see how existing proof could help. But with some example, I realized yes, it can be.
Who else? Another PhD student. Where's that? There's some PhD students there, weren't there? You were the sort of maybe camp, weren't you?
I'm not a PhD student.
PhD student. What about you? What did you think?
Might be useful.
Yeah. Can you see where it might be useful?
You have a lot of set space. You can use some kind of 3 sets, 2 sets or something.
Other people?
Again, I don't really know enough about it, so, I mean, is it like a general term that means a lot of different things, or is it essentially just learn on a training set and then apply that to test set? I mean, is it that obvious, is it that kind of easy to say, or are there loads and loads of different ways of doing it?
It is machine learning in general can be split into different camps, but the 2 big camps are symbolic machine learning, and this is what Alison is approximately doing. Symbolic meaning it can give you a symbolic result, for example, a new statement, a new lemma, if you like, on the basis of seeing lemmas already. And the other camp is statistical machine learning. This is what Joseph and I are doing. This wouldn't give you a result in the form of a formula. This would give you a result in the form of a probability number, saying that with some probability this is true, or Because for some probability, this lemma can be used in the proof of that lemma,
Yeah.
or something like that. So yeah, and it depends what you want from your symbolic machine learning system, because the restriction on the symbolic machine learning in our area is that obviously you cannot expect the system to formulate a new generalization of a lemma for any CEV.
Yeah.
And because we are talking about now coming to almost to a halting problem, you cannot expect an algorithm that would be able to formulate any statement about anything for you. And with with statistical methods, you probably have no restrictions on the theory, on the library you can apply it to. But then the result is much a weaker statement. It's just a probability of yes, no,
Yeah.
rather than an answer, a new lemma or something.
Yeah, the sort of system that I've had experience with, it doesn't train, you don't have a set of positive and a set of negative examples. It's more exploratory. So the tagline for it is, you don't know what you're looking for, but you know you found it.
Right.
You're looking for something that's interesting, but you don't know what yet. You don't
Okay, so
want the concept.
how do you measure interesting? Like, what, you know?
Sorry?
How would you measure interesting? You know, what?
Okay, so, well, humans, however we do it, I don't know how we do it, but the system does it. It's based on a set of weighting criteria which are supposed to reflect ideas that we find interesting, or aspects of interesting to you, such as being very simple, maybe being surprising, maybe applying to lots of things, or maybe applying to hardly anything, and those kind of measures. And it just calculates it as a weighted sum which you set at the start of the run. You set only for surprising things and spit out.
Any more questions from PhD students? Oh, well, let's throw it open to people who aren't PhD. Hello.
I've got a question actually to Joseph. I read your abstract this morning, and you made a statement which is, roughly speaking, you also want to formalize notions in physics and chemistry in the sciences.
Oh, I made a very provocative motivation.
No, actually, I'm very.
Oh, Hilbert was actually interested in that.
Okay.
Hilbert was trying to do axiomatics for physics.
Yes, but this goes, in the historical context, this goes back to one of Hilbert's problems. He tried to axiomatize physics, and I think the consensus is that it's not a well-posed problem. Would this be an obstacle to?
It's not what?
It's not a well-posed problem?
Well-posed problem?
Yeah.
I haven't done it, so I can't really comment too much on it.
Right.
But
you did list it as an aspiration, so I was wondering.
Yeah, and I think for a good reason, because that there is real lots of mathematics in these sciences.
Yes.
Like you will hear Manfred tomorrow talking about economics, and it's an interesting question. Like if you remove mathematics from these things, what do you get? What's the thing with which you are left? What's the other thing? So you can see that I'm a mathematician now. So for example, one thing which you might say would be left is the kind of thing, for example, Alison was talking about, this kind of inductive aspect, this reformulation of theories which we had in physics. We also have it in mathematics, like Lakatosh was writing about how mathematics changes gradually. So even there is a thinking, some people think in mathematics that mathematics isn't fully deductive. Already Poincaré was kind of arguing against full deductive understanding for formalization of mathematics. I think if we can do pretty strong automated reasoning for mathematics, then we will see what are the other things that these sciences like physics need, and that may pretty much be the inductive aspects. But that's what we are, in my opinion, also seeing in mathematics, that we cannot really do complicated mathematical theories just by brute force deduction. We need induction in some sense. So I think if we ever achieve, for example, proving, I don't know, Jordan curve theorem or ABC conjecture, or I don't know, strong mathematical theorems totally automatically, then going there, well, unless something happens with our computational power, unless we get quantum computers and we can do brute force search unlimitedly or something like that. While going there, we will have to develop methods which will also be useful for sciences like physics. But that's just my conjecture.
Currently in physics, there's a very large research area called axiomatic quantum field theory. So hidden quantum field theory, which is the study of particle physics, or the mathematical side.
Yeah.
The question is because experimentally it can calculate, I don't know, the magnetic dipole moment to 12 decimal places, but it's not been formalized rigorously in mathematics. So can you foresee your project to be able to contribute to a project like this in physics?
Well, I would like to say that yes, but I know how weak we still are. So we can do we can do quite a bit more than we were doing 10 years ago in these life theories, but it's still very little.
Right.
So going. I think the big progress is that the combination of automated and interactive theorem proving can really today dream about, like Hales is almost finished for formalizing the proof of Kepler conjecture, etc., etc. So I think, for example, the next project for Hales would be formalizing the proof of Poincare conjecture, which has been proved by Perelman like 10 years ago.
Right.
And that kind of leads in that geometry, like the things which physicists do.
I think, well, of course, you're going to get another answer to that question in the invited talk tomorrow morning, which isn't about physics, it's about economics, but it's the same. It's the same sort of thrust. Can we move these things out from mathematics to other areas? Other questions, comments? You see, the thing about this lecture theatre, it's very disconcerting, but you see, you can see everybody. So anybody who moves their hand, pick up their phone or scratch their ear or something, anybody down here can see them doing it. Think, oh, they must be trying to ask a question.
You can see everybody.
No.
We can't see.
No, we can't see. So other questions, comments.
Could I ask? You mentioned this notion of induction in some sense. Now, is this the kind of thing that Alison's talking about, trying to generate better and better conjectures, or is it something more open-ended?
As far as I understand, the way in which you meant it was the way in which I mean it as well. And maybe so in this in the systems I've had experience of, it's plain simple scientific induction. The conjectures were calculated empirically based on a database of numbers or groups or whatever it was. But yeah, the sort of reasoning that humans do, inductive, abductive, deductive, analogical, informal, all of these things, I don't think any of those are specific to science and then in maths. I don't think there is anything I think it's the type of reasoning is the same. So if we can model that, then we can model we can generate theories in maths or in science. It's the objects about which we're reasoning that differ.
Yes.
One question about the deductive method. Are you actually using deductive steps as well in this system, or is it just exploring in general?
The system does interface to theorem provers which use deductive methods.
Okay.
But it can run without that as well. So the system alone, I should clarify, I'm really talking about Simon Colton's HR system, which I then extended in my PhD. And so that itself didn't have any deductive methods in it, but like I say, it interfaced with systems which did. which you could run it as a standalone system, or you could run it as a part of a collective of systems.
So how was the prover used then?
The prover, if it generated it generated a conjecture which would prove all its examples, it could send it to a theorem prover and then see whether that was deductively true, and then it would become a theorem in the system. It would be more interesting.
Just
It would just become a proved theorem. Yeah.
Ah.
Have you found mathematicians yet who are eager, you can twist their arms to get mathematicians to actually use any of this technology?
I can give you a fresh answer. Also, last week there was the Dutch Mathematical Congress in Nijmegen, and we hosted Conway and we hosted Gauthier. And Gauthier gave, so George Gauthier is the guy Katja was talking about. He formalized, so that there is really a big mathematical theorem concerning classification of finite simple groups, which spans 2,000 of pages, and it's kind of famous in mathematics for being big and being understood properly by nobody. And Gauthier took it as one of his next challenges. So he really formalized the first step in the proof, which takes basically two graduate mathematical books. And he finished the formula with a big, some team of people in 2012. And now he was at the Dutch Mathematical Congress giving the talk about it to mathematicians. And for example, Conway was definitely interested and asking questions, etc. Although Conway probably isn't in the age where he would actively start using these systems. I think the mathematicians are interested. There is another case, and that's even bigger case, and that's this Tom Hales, who actually proved something himself. He proved 400 years open conjecture called Kepler conjecture. And the problem with it is that these proofs are in computational geometry are becoming more and more software assisted. And it's really hard for the human referees to check whether the software did the work correctly, or whether there was a trivial bug which just helped you to prove some conjectures or lemmas which are false. And basically the only way how to verify this is to use computers again, to use proof checkers. So if you want to do computational geometry these days, so somehow you have to persuade the others that you are doing it correctly using the software, and you using automated reasoning and verification.
I think we organised a workshop in Edinburgh just about a year ago, wasn't it? When we got mathematicians, local mathematicians who happened to be around, and people in verification together, and I found it rather very interesting how the mindset of the mathematicians has shifted, because if you had such a workshop 10, 20 years ago, the senior mathematicians would be just saying, oh, this is just a joke, go away. And so Michael Attia, who's a very distinguished mathematician in Edinburgh now, aged about 80, you know, he wrote rather vociferous articles in the early 90s about how this was just silly, roughly speaking. And people's minds have shifted. It wasn't necessarily that they were going to use this stuff themselves, but the work of Hales, the work of Gontier, had made them realise, well, this was something that people needed to be aware of. And so then we had discussions about what kinds of things would mathematicians like to see happening. And they said, well, you know, we think our graduate students should know about this stuff. You know, wouldn't it be good to, one of the things that mathematicians said, you know, people have, sometimes it's rather hard to teach people about proof. You know, if you had stuff that could help grade people's lousy attempts at proof and so on. Now, of course, that was what they were saying. Whether if you produced that thing for them, they would actually use it was a different question. But I think the mindset is definitely shifting. And the fact that, as you say, you know, people have big mathematical congresses and invite Gontier or Hales to come and speak.
We actually have one mathematician who is using this technology in this room, and this is Jonathan. So he's a mathematician by training, and his thesis was about organization of mathematics in such systems. And Jonathan, if you can Because when we constructed this methodology, Jonathan tested immediately all this on the problems he had when he was doing his PhD thesis. So if you could maybe tell.
Well, one of the problems for mathematicians to use this kind of system is that, for instance, to formalize one page of undergraduate textbook, it can take more or less 1 week of work, of one person working 6 or 7 hours. So it's a lot of work, and this kind of tools can automate parts of these proofs are necessary in order to get mathematicians to work in this context, because otherwise, if you are trying to prove something, for instance, in group theory or algebraic topology or something like that, and it takes 2 or 3 weeks to start formalizing just the most basic results, you can get a bit upset and say, well, it doesn't worth my time to invest so much time doing this. So this kind of tools that in some way automate and that help you to improve your performance when you are proving are necessary, I think.
Other questions, other comments?
Yeah, with your classification of learning, one can also look at it from a different way. So I come originally from the AI angle with that, so to see how does the human mind actually achieve that. And when you look at theorem proving, then obviously we learn when we are newcomers and whatever, very slow at proving things, and then improve and get deeper and deeper into how to say a certain area. And so obviously we do that. But then when you look at machine learning, they're the ones that are oriented, how to say, to how do humans do that, and we try to simulate that. And there are other methods like statistical methods, I guess, are not of that type. And according to that, do you see any, how to say, need to go beyond statistical methods, or would you say that's it?
Well, I always was interested how well the statistical machine learning methods actually emulate what we call intuition. That is, when we come to a mathematician and say, would this theory be proven or not, he may just by looking at this say, no, I don't think, or yes, yeah, that might. And we ask why. He says, well, it just feels like it. And what is this feels like it? It's years and years of experience, and this is in a way statistical knowledge, because it's accumulation of a lot of different instances of similar lemmas, or maybe not quite similar lemmas. And in a way, it is a statistical accumulation of knowledge that gets transformed into what we call an intuition. And yeah, what we're trying to do is essentially capturing this kind of intuition. Yeah, this is proven because the other similar thing is proven. And it's amazing that, you know, we're working on this only for 1 year, and we're able to find very interesting analogies between completely different mathematical theories. And this is encouraging because there is something of from statistics in this. Obviously, I'm not saying that you can cover everything by statistics, but there is some elements to it, it seems.
Sure, well, not doubt it at all. There's a lot to it.
Yeah, and for me, it's a key motivation is to find out how humans are doing things. And I guess I kind of work both ways around. So I think working out how humans are producing maths will help us to create better automated mathematicians, because they'll produce a similar sort of output to that which humans are producing. And vice versa, creating the computational tools will help us to understand how humans work as well. And Ursula and I are conducting lots of ethnographic studies into sort of what we call backstage mathematics, so things that go on behind the scenes before the lovely final publication and great proof arrives.
I think that this kind of distinction between symbolic and statistical, well, it's obviously useful, but my machine learning is kind of pretty rusty. But I think I've seen some theorems. For example, when you take neural network, which might be considered to be on the statistical side, then you can extract rules from it. So you get something which looks symbolic to you. So it's well, internally I could tell you you are just a neural network, but well, I mean externally, but internally you think I have concepts in my mind and I can do induction, etc. So I think it's useful to use these concepts like statistical machine learning and symbolic machine learning, but these methods, I think that there is a continuum of them, like Alison said that she also uses weights for example. So how do you assign the weights? You can use the statistical machine learning methods to assign the weights to tune it for a particular domain, I guess. Or I don't know, negative or positive examples. You can also do ILP using negative or positive examples, etc. So it's and I think especially now that we really have the deductive capabilities linked to it, that then, well, again, the symbolic part becomes very, very strong because we are just running a very strong symbolic machine to confirm our conjectures. So you could consider it that it merges the statistical machine learning with some symbolic AI. I think the interesting things are really in the combinations of all these methods.
Okay, other questions? Oh, we've got run out of time. I was going to say, the more we talk, the further we are from the bar, but that's not right. The more we talk, the further we are from the poster section. Well, anyway, thank you for our panel. Thank you for the panel for
I think it's poster session, and it ends approximately in 1 hour, and then at 7 we have dinner, those who come for dinner.
Tell us where dinner is.
It's Apex Hotel. I suggest you to look at the map on the web. The Main Street Workshop has a map. If you don't want to look at the map, right, you don't want to have a look at the map, you'll have to listen for 15 minutes to explanations of turn left, turn right, and take notes of it. So it's roughly, if you can imagine the bridge, the tail bridge, not the rail bridge, but the bridge for cars, and the university on the right side from that bridge. So the Apex Hotel is just on the left side from that bridge, so you have to reach the bridge somehow and go to the opposite side from the university of that bridge.
Don't fall in the roadworks on the way. Locals will know what I mean.
You will see Apex Hotel. It's just near the waterfront.
Or look on your telephone.
How long is the walk about?
Huh?
How long does the walk take?
You have to apply little machine learning algorithm to find it.
It will start with reception, so if you're a little bit late, you'll be all right.
Good.
It's about 20 minutes, I will. Quite fast.